We're looking at a paper today called Ask, Don't Judge, Binary Questions for Interpretable LLM Evaluation and Self-Improvement. It's by Sang-Woo Cho and a team of researchers at Capital One.
Yeah, and this one is a big deal.
Huge deal. So here's the core insight for you right up front. The current LLM as a judge paradigm is just structurally broken. When you use a model like GPT-4 or, frameworks like Geval to score an output, you receive this opaque, holistic scalar like a 4 out of 5.
Right, a total black box.
Exactly. And that number suffers from severe ceiling effects. These models systematically award perfect scores to text that is highly fluent and semantically plausible, even when it contains total factual fabrications. So this paper introduces Bineval. It's a training-free framework that forces the evaluator LLM to decompose complex evaluation criteria like factual consistency or coherence into atomic, binary yes or no questions.
Which fundamentally changes the math.
Right. By independently aggregating those Boolean verdicts, Bineval matches or outright beats trained baseline models, it solves the opaqueness of LLM judges. And because you suddenly have granular question-level disagreements, it allows for automated programmatic prompt optimization based on explicit failure modes.
Which is exactly what you need for a production pipeline.
So welcome to AI Paper Slop, where we tear down the latest ML research to see what actually moves the needle in production. If you are building evaluation pipelines right now, they feel a bit like rolling loaded dice.
Oh, absolutely.
You tweak a prompt, you run your evil set, the average score drops by 0.2, and you have absolutely no programmatic way to find out why.
Yeah, and the bottleneck we are hitting in iterative model development is entirely tied to this diagnostic fidelity. I mean, we treat human evaluation as the gold standard because humans can explain their reasoning.
Right, they can leave notes.
Exactly. But putting humans in the loop is completely incompatible with agile engineering. You cannot wait 2 weeks for human annotators to return a consensus score every time you test a new decoding strategy. Or, adjust your temperature, or push a slight commit to a system prompt. The iteration cycle demands automated evaluation.
And we all know traditional lexical metrics are just dead in the water for modern open-ended generation tasks.
Completely dead.
Like Enneagram overlap metrics like Rouge or BLUU, and even early embedding-based metrics like BERT score, they are fundamentally blind to semantic correctness. They measure surface-level similarity.
Yeah, they don't actually read the text.
Right. So if your summarization model outputs the stock market crashed on Tuesday instead of the stock market surged on Tuesday, Rouge gives that a near-perfect score. Because the Enneagram overlap is incredibly high, completely ignoring that the factuality is inverted.
Which is exactly why the industry wholesale pivoted to using LLMs as judges. I mean, frameworks like Geval, Alpacaival, or MTBench became the standard practically overnight.
Oh, for sure.
You feed the LLM the source text, the generated output, and a rubric, and ask it to output a score from 1 to 5. But the structural flaw in that approach is the scalar output itself. It compresses a massively high-dimensional evaluation, space fluency, relevance, factual fidelity, tone into a single integer.
Yeah.
When an engineer sees a generated summary drop from a 5 to a 3, that integer contains 0 actionable gradient. Like, is the summary suffering from a factual hallucination? Did it drift off topic? Is it missing key entities?
It's like a professor handing back your final essay with a giant C on the front, but absolutely no red ink in the margins. Like, how are you supposed to debug that?
You can't.
You just can't. You are left guessing which paragraph ruined your grade.
So what does this all mean for iterative development?
Well, it makes A/B testing prompts or decoding strategies nearly impossible. And worse than that, a C- from a professor is at least a somewhat deterministic failure. Holistic LLM judges give you a stochastic failure driven by severe biases.
Right, the ceiling effect. Exactly. The authors heavily document the ceiling effect inherent to these holistic evaluators. LLMs are highly susceptible to verbosity and fluency biases. Because they are fundamentally trained to predict the most probable, natural-sounding next token, their internal activations heavily weight fluent, well-structured text.
So they get distracted by pretty prose.
Pretty much. If the generation sounds professional and authoritative, the LLM judge glosses right over the factual inconsistencies and slaps a 5 out of 5 on it.
Which brings us to Bineval's core philosophy, Ask, Don't Judge. If a single holistic score is a useless diagnostic, we have to physically force the model to show its work. And Bineval does this with a 3-step pipeline.
Right, starting with the meta prompt.
Yeah, step 1 is the meta prompt. It ingests your specific task. So let's say it's abstractive summarization, and it summarizes the task requirements. Then it explicitly decomposes those broad requirements into a list of atomic Boolean yes-no questions. And these are grouped by evaluation dimensions.
You get clusters of questions.
Exactly. A cluster for fluency, a cluster for coherence, consistency, and relevance. And, crucially, the meta prompt explicitly generates violation examples for the negative cases.
Which is such a smart move, because those generated violation examples act as few-shot negative constraints.
Oh, interesting.
Yeah, if the meta prompt generates a question like, are all named entities accurately represented? It also generates a synthetic example of a failed entity translation. So the evaluator model has a localized anchor for what a zero looks like in its latent space.
Okay, let's unpack this for a second, because when I first read this, I thought, isn't this basically just chain of thought prompting dressed up in a fancy format?
I mean, it sounds like it on the surface.
Right. Like, we already know how to tell models to think step by step and list out their reasoning before outputting that final 1 to 5 score. Even if we break it into a 50-question compliance checklist, it is still using the exact same attention heads to read the exact same source text. So why wouldn't the fluency bias just bleed right into its answers for the binary questions?
That is the big question. And it comes down to how autoregressive conditioning works during the generation phase. Chain of thought allows the model to ramble toward a single holistic conclusion.
Because it's predicting token by token.
Exactly. When an LLM evaluates a highly fluent text using standard chain of thought, its early layer activations immediately recognize the structural quality of the text. Because it is predicting tokens sequentially toward an ultimate target score, those early good text activations heavily bias the probability distribution of the subsequent reasoning tokens.
Oh, wow.
Yeah, it ends up generating a chain of thought that merely justifies the 5 out of 5 it was already leaning toward, completely ignoring that it hallucinated a date halfway through the text.
So the reasoning is downstream of the vibe check.
Precisely, which is the opposite of what we want. Bineval severs that autoregressive dependency. In step 2 of the pipeline, the evaluator LLM is not allowed to write a cohesive essay evaluating the text.
No rambling allowed.
Right. It is forced to evaluate each generated atomic question entirely independently. It must output a strict 1 for yes or 0 for no, accompanied by a brief natural language explanation restricted to that micro question.
So you are isolating the attention mechanism.
Exactly. When the model is forced to answer, is the date consistent? Its attention heads are functionally masked to only attend to the temporal tokens in the source and the generation. The overall fluency of the surrounding text basically loses its weight in the probability distribution for that specific binary gate.
That makes a ton of sense. And then in step 3, Bineval just averages those binary verdicts to create a per-dimension score between 0 and 1. And the data backing up this isolation mechanism is staggering.
It really is.
They tested this across SumEval for summarization, topical chat for dialogue, and QEGS for hallucination detection. On the SumEval consistency metric, Bineval using Claude Sonnet 4 achieved an incredibly high 0.655 Spearman correlation with human annotators. UniEval and GEval weren't even close.
Not even the same ballpark.
Yeah, and even when they swapped the evaluator for an open source model like GPT-OS 120B, Bineval still destroyed the trained baselines.
The aggregate numbers are impressive for sure, but the Russian Su-27 case study in the paper is what truly exposes the mechanics of why holistic evaluators fail. It's the perfect microcosm of the problem.
Oh, let's talk about that one. That was a wild example.
Yeah, so the source text for one of the summarization tasks was a news article detailing a U.S. military RC-135U plane being intercepted by a Russian Su-27 jet over the Baltic Sea.
Okay.
The source text makes 2 very distinct points. The Pentagon called the intercept unsafe and unprofessional, while the Russian Defense Ministry stated the jet was scrambled merely to identify the aircraft.
So we have 2 distinct geopolitical entities providing 2 completely different accounts of the exact same event.
Exactly. The generation system then produces a summary, but the summary hallucinates the attribution. It claims that the Pentagon said the Russian jet flew around to identify the plane.
Oh.
Yeah, and furthermore, it appends a completely fabricated URL dailycaller.com to the end of the text, which did not exist anywhere in the source article.
It conflated the actors and hallucinated a citation. I mean, to a human, this is a catastrophic failure in factual consistency.
Absolutely. But when they ran this through GEval and UniEval, Both of those baseline evaluators gave the summary a perfect 5 out of 5 for consistency.
Wait, really? A perfect 5?
A perfect 5. What's fascinating here is how clearly we can see the LLM falling for semantic plausibility. The summary contains the correct entity tokens: the RC-135U, the SU-27, the Baltic Sea, the Pentagon. The grammar is flawless.
So it looks right at a glance.
Exactly. To the attention mechanism of a holistic judge, the dense token overlap between the source and the generatand triggers massive probability spikes for a high score. The model feels that the text is topically coherent, so it completely suppresses the localized factual mismatch regarding who said what. And it ignores the hallucinated URL because, well, URLs look natural at the end of news summaries.
It passes the vibe check. But Bineval doesn't ask for a vibe check. It doesn't ask, is this consistent? Instead, for the consistency dimension, it generated 7 targeted binary questions.
Right.
Question 1 asks about claim support. Question 2 explicitly asks about fabrication. Question 3 asks if the entities are accurate. When forced to isolate its attention solely to question 2, the Bineval framework easily spots that the URL string does not exist in the source context and outputs a 0.
Because it's not looking at the pretty grammar anymore.
Exactly. And when it evaluates questions 1 and 3, the localized attention catches the subject-predicate mismatch, that the Pentagon did not say the jet was identifying the plane, Russia did, so it flags a 0 for both of those. Out of the 7 questions, Bineval answers yes to only 3. It scores the summary a 1.57 out of 5.
And the human annotator scored it a 2.0.
Unbelievable. Bineval perfectly mirrored human judgment by dismantling the text into Boolean logic gates.
Yeah, and this raises an important question, right? Like, what is the fundamental mathematical mechanism making these binary questions so much more robust? It is not just that checklists are organizationally helpful for us humans.
There's real math happening.
Yes, there is strict statistical rigor operating under the hood, which the authors classify into 2 major mechanisms: complexity reduction and variance reduction.
Let's dive into the complexity reduction first. Because asking a model to rate factual consistency on a scale of 1 to 5 is a massive computational burden.
Oh, huge.
The LLM has to simultaneously map the source text, map the generated text, evaluate entities, check numbers, track causality, scan for hallucinations, and then somehow project that multidimensional error space onto a one-dimensional scalar integer.
It exceeds the reliable processing capacity of a single forward pass.
Yeah.
You just can't fit all that logic into one pass. But asking, are all named entities accurately represented, fundamentally restricts the computational subspace.
It narrows the focus.
Right. The attention heads no longer have to balance grammatical fluency against causal logic. They execute a highly specific token matching and semantic verification task. And that drastically reduces the probability of the model hallucinating its own evaluation.
And then there is variance reduction via aggregation. Here's where it gets really interesting. We are basically building a random forest out of LLM prompts.
A random forest is the perfect way to visualize it. I mean, when you aggregate a series of weakly correlated binary classifiers, you mathematically reduce the variance of the overall prediction.
Right.
The authors proved this by plotting the pairwise phi coefficient correlation matrices for the binary questions. The phi coefficient measures the association between 2 binary variables. If 2 questions have a high phi coefficient, they're essentially checking the exact same thing. But Bineval's questions are remarkably decoupled.
Yeah, look at the fluency dimension data. Bineval checks both spelling, which is question 2, and punctuation, which is question 3. You would think those are highly correlated, but their phi coefficient is a new 0.02.
That's crazy low.
Right. They are basically orthogonal vectors in the evaluation space.
Which means they are catching completely disjoint failure modes. The joint probability of both failing is independent. Like a text generation can have perfect spelling, but be entirely devoid of periods and commas, or vice versa.
Right.
If you use a holistic prompt and just ask, is it fluent? The model anchors on the high-quality spelling, and the overall distribution just glosses over the missing punctuation. By explicitly forcing decoupled classifiers, the math guarantees that your aggregated score has lower variance and much higher recall of localized errors than a monolithic pass. It enforces explicit coverage over the entire failure space.
So what does this all mean for the engineering lifecycle? We now have an incredibly potent diagnostic tool. We don't just know that a summary scored a 3, we know it specifically failed. Question 1 regarding entity misattribution, and question 2 regarding hallucinated URLs.
And that data is gold.
Yeah. The Capital One team takes this granular Boolean failure data in section 3 of the paper and uses it to close the loop with automated programmatic prompt optimization.
This is where it gets super practical. This shifts Bineval from a passive metric into an active self-improvement engine. Because your feedback is atomic, you can compute exact, localized disagreements between models.
How did they set that up?
They ran a cross-model update architecture. So they used a massive, highly capable model, Claude Sonnet 4, as the reference judge, the gold standard. Then they used a weaker, 120 billion parameter open source model as the target judge. And they ran both models over the evaluation set.
And because the evaluation is decomposed, they aren't just looking at a delta where Claude gave a 4 and the open source model gave a 3.
Right, that wouldn't help.
They can see that the models agreed perfectly on questions 1, 2, and 3, but disagreed precisely on question 4, which dealt with informational omissions.
Exactly. They isolate that exact disagreement and feed the source text, the generated text, and that specific binary question into a third LLM, which acts as a note-taker.
Okay, note-taker.
Yeah, and the note-taker's job is to analyze the delta and figure out why the weaker model failed the gate that Claude passed. It extracts a generalized lesson. The system then deduplicates these lessons across the entire data set. And finally, a meta prompt automatically rewrites the weaker model's system instructions to patch the blind spot.
The example they highlighted in the paper is brilliant. The weaker 120 billion parameter model was constantly penalizing summaries for being too brief. It was fundamentally confusing the concept of leaving out background info with factual inconsistency.
A very common failure mode, honestly.
Yeah, and the cross-model loop caught this disagreement specifically on the omission-related binary gates. The note-taker model extracted the lesson, and the system automatically injected a new rule into the weaker model's prompt: omission does not equal inconsistency.
Such a simple fix.
Right. That single string of text fixed the semantic confusion. The weaker model stopped penalizing concise summaries, and its Spearman correlation with human judges jumped by a massive 0.136.
And at 0.136, improvement on consistency, just from an automated cross-model text update, is a huge leap forward. But, the authors were rigorous enough to test the absolute limits of this self-improvement loop.
They pushed it until it broke.
They really did. They took this automated prompt updating system and ran it on IFBench, which is a benchmark specifically designed to test instruction following. And they hit a very hard architectural ceiling on what you can actually achieve by just dumping lessons into a system prompt.
This is the prompt bloat problem, and honestly, it is mandatory reading for anyone listening who relies on automatic prompt optimizers like DSPy or OPRO.
Yes, 100%.
So the IFBench dataset separates tasks into two categories: promptable constraints and computational constraints. For promptable constraints, things like formatting, plain text requirements, or dictating sentence structure, Bineval operated flawlessly. The note-taker extracted lessons, updated the prompt with instructions like output must be plain text with no markup, and the model obeyed. Accuracy on those constraints jumped by 17 percentage points.
But then you hit the computational constraints.
Oh boy.
These are instructions like maintain an exact word count of 250 words, or ensure the ratio of verbs to nouns is exactly 1 to 2.
Tasks that LLMs are notoriously terrible at because of their autoregressive architecture.
Exactly. When the weaker model failed those computational constraints, Bineval correctly diagnosed the failure. The note-taker model generated perfectly accurate lessons. It wrote instructions like maintain a running counter for each required element and stop when the target count is reached.
Sounds logical.
Right. The system faithfully appended that lesson into the generation prompt, but the LLM simply could not execute it.
Because you can write maintain a running counter in a text prompt all day long, but a standard transformer model literally does not have a computational scratchpad in its forward pass to store an integer counter. You are adding dials to a machine that aren't hooked up to the engine.
That's a great way to put it. If we connect this to the bigger picture, automated prompt optimization only works when the model already possesses the latent capability in its weights, but just needs better alignment or structural guidance to surface it. You absolutely cannot prompt an LLM into possessing raw algorithmic or computational abilities that run counter to next token prediction.
And the mechanics of what happens when you try are catastrophic. As the system continually tries to fix the failing computational constraints, it just keeps extracting more lessons and shoving them into the prompt. The authors documented the IFBench meta prompt ballooning from 22 characters to over 6,200 characters across just 4 iterations.
Which causes severe attention dilution. The attention mechanism in a transformer computes a softmax distribution over all the tokens in the context window. As you dump 6,000 characters of unactionable instructions into the system prompt, that softmax distribution physically flattens out.
The signal gets buried.
Yes,
Ah.
the mathematical signal of the promptable constraints, the formatting rules that were actually working, gets completely lost in the noise of the useless computational lessons.
The performance data shows the exact moment the attention mechanism collapses. By iteration 4, the overall accuracy actually degraded. The count constraint accuracy collapsed from 63% down to 31%. The prompt optimizer literally cannibalized the model's context window and destroyed its baseline performance.
It is a profound warning. Diagnostic data is incredibly powerful, but blindly feeding that data into a prompt optimizer without understanding the architectural limits of your foundation model will degrade your pipeline.
Wrapping this all up for the engineers listening, Bineval provides a task-agnostic, training-free framework that fundamentally shifts evaluation from a vibe check to a rigorous diagnostic. You are making a trade-off, though. You're sacrificing a bit of computational efficiency, making multiple localized LLM calls to traverse these binary gates instead of a single holistic call.
But in modern iterative development, inference compute is incredibly cheap, while high-fidelity, actionable diagnostic data is the most expensive bottleneck in the pipeline. Spending a few extra fractions of a cent per eval to know precisely which orthogonal failure mode your new decoding strategy triggered is, frankly, the highest ROI trade you can make.
Before we wrap, I want to leave you with a final provocative thought to ponder. We just spent this entire deep dive looking at how breaking evaluation logic down into strict atomic binary gates forces explicit compartmentalized reasoning and prevents the attention mechanism from glossing over factual errors.
Right.
So if this Boolean decomposition works so well for verifying text, could we reverse engineer this framework into the generation side itself?
Oh, that's interesting.
Imagine a transformer architecture where the LLM isn't just freely sampling the next token. Imagine if it is mathematically forced to implicitly answer a strict latent space binary checklist verifying entity consistency, causal fidelity, formatting before the logits are allowed to pass through the softmax layer. What if we took Bineval and pushed it down into the core generation loop, turning autoregressive generation itself into a verifiable compiled process? Think about the implications of that for hallucination-free generation. Until next time.